Anyone wants to come up for the question? 50 stickers question. Do the transfer curve and the half circuit. 25 each. No? No one wants to try. So let's give you some time to think about. Someone wants to come up and answer the question. But what we're going to do today is, as I said, we're going to wrap up chapter 10 on differential pair. And then we're going to dive into the frequency response next week. For 3 weeks, I think it's probably sufficient to discuss just a preliminary discussion on frequency response of circuits. But hopefully we can wrap up the discussion of differential pair. We have already established the idea as the reason why you want to have a differential pair. As I said, typically what happens is that your noises in the system are common mode to the circuit. So the idea is that if I build a identical system and give them the same input, I can sort of cancel it or suppress the noise propagation in the circuit, and then allow the signal to be deliberately input to the system through differential operations, so that you can separate signal from noise. That's the basic idea. And there's, of course, a lot of things to think about or to evaluate in a differential circuit. So we're going to go through that, and there's variation of those. And there's, of course, this is like, I always use the example of sort of like building a house or an architect, is that if you go to look at other design, there are always reasons for a particular design. So we're going to talk about a different type of design. For example, if I'm doing a circuit, this is a typical, the most simple, straightforward half circuit, a MOSFET differential half circuit. We already know it's transfer curve, we talked about that. And when you build a half circuit, the basic idea is that for differential, if you consider differential half circuit, meaning that we'll only consider differential signal, therefore you're setting your common mode signal to 0. Therefore, because you're not lifting the idea is that you're not lifting your seesaw, therefore this node called the VS should be, we can view it, this is the VS node. And we view it as a differential, I should say it's like AC ground. This is ground. Consider a virtual ground node called the virtual ground node. If you're considered for what signal? For particular signal, for VID. If you consider differential signal, this is AC ground. So if I'm only consider differential signal, then I could view this node as virtual ground. Therefore, we could quickly get the differential gain. Or let me do not use this. I could quickly get VO1. This is VO. Let's say this is. I can get the relationship between VOD and VID very easily through this operation. So this is simply a common source amplifier. So we know that its gain is, small signal gain should be minus GMRD, right? So this is very simple. If I can look at the circuit and view it as an equivalent half circuit, and you can see that for differential signal, it will then be amplified by a common source stage. Then this is your gain, right? So what about the circuit on the right? What do you think will happen? First of all, for transfer curve, we expect that I'm not doing inverting operation, then you will still assume. Anyone wants to come and do the thing? This will be VID, and I will also label my VID max minus VID plus. So you're expecting your circuit to be at a balanced state because I'm having half the current. So you're assuming that this node, the current's coming down, is actually balanced. Therefore, what determined the differential signal in this circuit? Any thoughts? VOD. What is VOD? If I write down the definition of VOD, it will be defined as, let's say, VO. Let me just do the inverting here. Let's say if I define this as positive, so when will this be 0? When will this VOD be 0? When there's no current flowing through the resistor, meaning that I have current only going downwards. So each of them separate, each of them are account for half of the circuit. So when there's imbalance, meaning that if this device takes on more circuit, more current, the current has to flow over from here to make sure that some of them will come in this direction. Okay? I don't want to give out the answer, but just to give you a sense as to where your initial point is. If you're at a balance point, meaning that this part, let me just give the 1 point. So basically what you want is to find out the extreme node, extreme term, and also the balance node. So I'm giving the balance node at VID equals to 0. This simply means that ID1 equals to ID2 equals to 1/2 ISS. Therefore, if you think about current going through, let's say if this is the current, IRD, let me just highlight it as I1. The currents are balanced, therefore I1 equals to 0. So your starting point is at the center, so it's at the center. Okay? And then you need to know which way does it go. If it goes high, what is the extreme level? If it goes low, what is the lowest level? Okay. So I'm going to leave you to think about what is the ultimate, what is the actual answer of that transfer curve, and also what is the equivalent half circuit. Okay. So let's go back to our discussion as to in most of the integrated circuit, as I said, you actually don't want to have resistive load because resistance are very expensive in integrated circuits, very hard to make. And it is an expensive component. If you don't need them, you want to do it with substituted transistor. Transistors actually come in handy in integrated circuits. So we talked about how we could do active load. So we talked about an idea. I want to sort of review this again. So we're going to do a more extensive study on differential pair with, we call the active load. This is to solve two problems. One is I don't actually want a resistive load, active load of, to be precise, I'm using a current mirror. Instead of using current source, you can use current mirror to realize that architecture. So let's go through a more detailed understanding of how it works. And large signal analysis, small signal analysis, what problem does it solve and what is its balance state? You also want to do the transfer curve to find its balance state. Okay? So it actually solved two problems. It actually increased multiple, I should say, features. It uses transistor. Transistor has loading devices. So in this case, I'm using for PNP or P channel. And then you could actually do a differential. If I don't want fully differential, I can do differential to single end and conversion. We talked about that. Meaning that you don't need to take out, you can only take out one, but without losing the gain. Maintaining a high, you do not lose half of the gain. If you only simply take out one node, then we're losing half the gain. So we can do a more effective conversion. And then lastly, it will actually improve. I will give that to set your output actually has a benefit to set output DC level. And talk about that. And this also lead to decrease of common mode gain. We're going to talk about that in a little bit. With the decrease of common mode gain, so this will be your differential gain can maintain with double the, if you compare to that with simply take out the one of the terminal, you actually maintain a high differential gain. Decrease this will simply imply that I would then have a common mode rejection improvement. Let me leave it here. So CMRR, that's the results would then increase effectively. Okay, so we're going to talk about why, and let me draw the circuit first and then do some simple discussion, or qualitative discussion first. So we start with a current mirror load. I want to emphasize the difference between, if I'm simply doing PMOS load and current mirror load, the difference between the two. If I'm doing current source load like the above, my current from the top will always be the same. In this case, because this node, this is V, we can talk about that in a bit. The difference is that this node is actually controlled by the ID4, I should say, M1, M2, M3, M4. If I do not do this connection, I'm connecting this all the way. Remember, if I'm doing current source load, meaning that the current coming down will always be the same. And let's say it's half ISS. But if I'm doing this, meaning that Vx, this X node, changes with ID3, which equals to ID1. So I can modulate ID1 and the Vx actually floats, so the current coming down can be determined by the floating of Vx. So you'll see that in just a minute. So this node will not be a fixed voltage. It's not the same as a common current source load. If you're using current source load, your base voltage, or I should say gate voltage, is fixed. In this case, this floating is being controlled by current on M1. So this is the main feature of having active load than passive load. That's even though it's an active device, it's still called a passive load because it does not changes with your input change. Okay, let's say this is still ISS. Okay, so we talked about conceptually how it functions and the small signal analysis. So if I'm simply wanting to look at its differential gain, meaning that if I'm doing small modulation on both sides, let's say there's a plus delta V, there's a minus delta V. So what do you expect is that the current here will be 1/2 ISS plus a delta I. And this current will be the same as this current, ID3. So your balance level plus a delta I, right on the left. And because this node is determined by M3, right, the overdrive on M3, so this node will actually be lower in order to support this increase of current. So it will actually map all the way to here. So whatever current is being supplied on the right, being set on the left will be mirrored to the right. And then because of this, this current will actually be reduced, right? Because I'm reducing its overdrive by its gate voltage. So this will be a minus delta I, corresponding to a minus delta I. Therefore, you will see that the current going out will be 2 times delta I. And we know that simply assuming that delta, this is a small signal, so it'll be minus, it will be a GM delta V. So my output, my voltage output VL, in small signal consideration will be delta I times output resistance. And using the half circuit consideration, you can assume that this is minus GM, as I said, RO2 in parallel RO4. The output terminal, we can view it as a half circuit. This is still virtual ground at this terminal. So you can still view it as RO1 in parallel RO4. Okay? 2 times, sorry, divided by your input is 2 delta V. So I skipped a few steps. To get rid of the 2, okay? So we get our differential gain, VL, in response to VID, which is 2 delta V. This is VL. Okay? So you still get, you're not getting the half, I'm getting the full. So without 1/2, you get the full differential gain. So this is the benefit of you convert it to single end and without losing half of the gain because we mirror it through M3 to M4. Good? Okay. So let's look at what the other benefit it has. One of the key important thing of this is that it actually allows us to have a better setting. Let's look at, it's set at DC level. What did I mean by that? Is that if you consider, if you set your VID to 0, that should be your VO output equivalent. At equivalent state, when you flatten your seesaw, what is the corresponding output? VO at equilibrium state or at its balanced state. So does anyone know how to approach in this problem? What do you expect this node to be at equivalent state? What do you think? So at equivalent state, if you think about it, if I need to plot, so what we want is to plot this. Because it's no longer differential, so you only want to plot VO, your output, against VID. So when VID equals to 0, we want to know where it starts. It's called the DC level, output DC level. So what determines output DC level is that the basic idea is that at equivalent state, ID1 equals to ID2 equals to 1/2 ISS. And this also make ID3 equals to ID4. Okay? So that simply means that if I want, remember, when we go back to current mirror, what is the drain voltage that will make these two has the exact matching current? Remember? What is this voltage? Should be. No one remembers? We did the plot. So if you have a current source, what is the output voltage which will make the left actually exactly equals to left? When? When VDS equals to what? Or VS, in this case, VSD. Yes? Yes, it has the same overdrive, same VGS. So has the same VGS or VSG. So this would only happen, the equivalent state will make VO equivalent where left equals to right, meaning ID3. How did ID3 equals to ID4 is when VSG3 equals to VSG4. Okay? If you still don't remember we did the plot? Trying to find the point where I reference. The intersecting point is where your VSD equals to VSG on the left, okay? So this is when this node equals to this node where your current will be identical. So what will be at VSG equals to VSG4. So I know that my current, let me write down, at what current at this balanced current level. So VO equivalent at equivalent state will be VDD minus VSG4, which equals to VSD3. Right? At equivalent, we know that the SD, source and drain, it should be identical in all terminal. The biasing condition should be, so this node should equals to this node in order for the current to be identical. Okay? So this would then be determined by TP, threshold voltage of P channel plus an overdrive at equilibrium for P channel. Okay? So we talked about VOV, overdrive at VOV at equilibrium for P channel is defined as 1/2 ISS, so times 2, you get rid of the 2, mu P Cox, W over L. 3 or 4 doesn't really matter because we know 3 or 4 are the same. So that's for P channel. You can also do the overdrive at equilibrium, meaning at equilibrium simply means 1/2 ISS. ID equals to 1/2 ISS. This is when ID equals to 1/2 ISS. That's a balanced state, right? For N channel, it will be the same, 1/2 ISS, mu N Cox, W over O, 2 or 4, or 1 or 2, doesn't really matter. So the N channel, you get an overdrive on that. So we know that its balanced state started here, somewhat slightly lower than threshold, lower than VDD by a VGS. Okay? So if you want to do the overall curve, you want to know that I already know my balance point. The next one is you find equilibrium point. The next is when VID is much, much larger than its overdrive. We talked about that. So this is still the same. This should be, the turning point should be the same, 1/2 VOV equilibrium for N channel, right? Square root. The reason for square root is because the current is double. The current needs to carry. So we already know the boundary, the turning point and x-axis. So the thing is that you want to find out how does it saturate. So if you think about the first point is that when I have all the current, this simply means that all the current goes to the left. So ISS ID3 equals to ID4. Always, sorry. Let me start with ID1. We know that ID1 takes on all current, takes all the tail current. ID1 takes all current, and ID1 equals to ID3 equals to ID4. Right? The whole side is being taken by M1. So currents, all the currents are tilted to one side. And this is the same as ID3 and is being mirrored to ID4. Okay? Good. So once you have this, I should say, it's probably not a good way. Right. Okay. Let me not do this at the beginning. So what happened is that ID1 equals to ID3. So this would then set Vx to a lower, even lower level, to VDD. Let me write it down. And plus a square root overdrive P. Because it takes on all the current. So this would then set this level Vx to a very low terminal. This gate voltage will be lower down because it's taking on more current in order to support that. Okay? So if you look at the right, so this is the left branch. If you look at the right, what happened is that you're expecting, if I'm doing open circuit, so ID1 should equals to ID4, ID2. And we know that ID2 equals to 0. So if I have a transistor which has been already turned on, how do I make this ID4 equals to 0? What do you think? If I have a transistor, this gate voltage is very, very low, meaning that transistor is on. So what is the state which will make this ID equals to 0? How do I make ID4? So that means that this should equal to 0. So what is the point? What is the bias condition that will turn it? I'm already turning my gate on. This is very low. My transistor is already on. It's above threshold with a high overdrive. But then there's no current. How do I make that happen? How? There's two ways of cutting off. Remember, for transistor, there's two conditions that will determine your drain current. One is carrier, the other is electric field. You have a lot of carrier, you have to turn on the electric field. How do you turn off the electric field? So you make this VSD. The way to do this is to make VSD equals to 0. So you put this device into linear region, and this voltage go all the way high to VDD. Okay? So this can only give you consistent results when VSD equals 0, which means that VO is at VDD. Okay? So now we know that when it takes on all the current to the left, the only solution you have to maintain 0 current on the right is at VDD. At VDD meaning that there's no overdrive, no VSD, no electric field. This is turning on electric field, right? Even though my Vx is very low, so you get this, and then it goes down. The other problem is then, we know that once it passes, it should go straight, and there's a VO minimum. This is harder to determine in this circuit because it's not determined by a resistor. For a resistor, you simply look for voltage drop on resistance. Current times resistance get your voltage drop. But in this case, it would determine by the right-hand side. Let's try that. So we need to determine what is VO minimum. You already know, let me write down, VO max is at VDD. So VO minimum will be set by M2. What is the lowest point of M2? So let's think about it. This would happen when VID is much, much smaller than your minus. So you're going to the minus side where what happened is that ID1 I should say ID2 takes on all current, while ID1 will be 0. And this would then set your transistor M3 to 0. This would then set Vx to VDD. You're turning off the transistor, right? You're turning off this. This is 0. How do you turn it off? You turn off by shifting this all the way to 0. That means that my ID you shift it all the way to 0, so that means that you're okay? So how do you make it balance at this particular level? So it would then determine by external, this would then be off. You don't have any current coming up. There still need to supply ISS at the bottom. So the bottom ISS would then be supported by, I should say, VO minimum. Would then be limited by, I should say, source voltage. I forgot to highlight. There's a source voltage, and then you need to take on the overall overdrive. So that it will be limited by transistor itself. So transistor itself will then give you VO minimum. Let me write down the number. It's slightly more complicated. Plus a VOV equilibrium N. When it takes on all the current, this is when ID2 equals to all ISS. So therefore, you actually have a higher overdrive. So the lowest it can go will be limited by transistor M2 entering linear region. Okay? So this is slightly complicated. The only thing, I think the main important things I would like you to take home is, of course, find the balance point, find the high and the low, and what are the limitations on its highest point, and what are the points that make you enter the lowest point. Okay? So as I said, we already know that you could convert differential to single end with full differential gain. You're not losing anything. And then we're going to look at how you calculate its common mode gain. This is also a little bit complicated, but let's think about it. So when you do the folding in this case, you connect this node to this node. I'm folding, even though they're not identical, but you can fold them and connecting this node to this node. So if you're doing the folding method, or I should say, let's do the folding. So if you do the folding method, your common mode, let me get the common mode. Okay. So the circuit will look something like this, VDD. And then if I folded and connected the output together, on the left and the right together. This is VICM. This is VOCM. And then the bottom is RSS. Okay? And because I'm folding it, it should be double of that. So there should be 1 GM1 plus GM2. Okay? So I have a diode connected load on the left. Therefore, when I connect the output, two outputs together, my VOCM equivalent should be this. So this should be it looks something like this. This will be 1 over, this will be M3, this will be M4. So the equivalent circuit, if I do some transformation, we know that for diode-connected structure, the equivalent resistance, if you're looking in, here is 1 over GM3. This will be 1 over GM4. And because they're identical, so that this is common mode. I should say common mode equivalent circuit. If you want to analyze your common mode equivalent circuit, it would then become because I'm doing the folding method. This will be 2 times GM, assume GM1 equals to GM2. And if you're looking up, this is for N channel. And this will be 1 over GM P channel. This will be another 1 over GM for P channel. Right? So you can simply equivalent to that. Let me highlight my input and output. Right here. So the input terminal will still be here. If I'm looking at common mode signal, this will be VOCM. Okay? So apparently what you actually make your operating at common mode, you actually make your I should say even lower gain, if you can see by the diode-connected architecture. Let me write down the gain. So if you do common mode gain, simply be minus GM N times, let me write it down this. There's minus 2 GM, meaning N channels, either M1 or M2, they're the same, times this 1 over GM in parallel, therefore it will then reduce the resistance by 1/2. So GMP. And the bottom will still be 1 plus 2 GMN times RSS. Okay? So instead of having a high numerator, you have an even lower denominator. Numerator. The denominator is the same. So you're actually getting a much smaller common mode gain. Let's say if I have the same transconductance, typically it's the same. So this can be close to 0 or even close to 1 or even lower than 1. So you have a common mode gain which will definitely be much lower than its original. Remember, our original case is this is the differential gain. You actually have a lower common mode gain, which will actually increase your rejection ratio even further. Okay? So what we're going to do now is just go through an example so you get a better sense as to how to analyze this type of circuit and what are the key parameters to be obtained. So let's give an example before we move on to other discussions. So let's say I have a differential pair, once again with with active load, M1, M2, M3, and M4. Two PMOS current mirror load and a MOS differential pair. So V in 1, V in 2. That's my output. I only have one single-ended output. So I'm going to give you device parameters and also to determine differential gain, common mode gain, and of course balance level. So first of all, you need to determine mu and Cox. That's 200. I'm making it somewhat more imbalanced in this case. Have transistors at the bottom with a ratio of 5. And to balance out its overdrive, it's probably best to do this way. To balance out the overdrive, making PMOS compensate this lower conductivity of P-channel devices. I'm making it 4 times larger. For PMOS, that would then make my equivalent overdrive to be the same. Right? So then we also need lambda n equals to lambda p equals to 0.1. That corresponds to early voltage about 10 volt. So once we have these numbers, this is 1 million. So we want to find its differential gain. There's 3 parameters. One is you want to find differential gain, common mode gain, and VO at equilibrium. You need to find these 3 parameters, 3 characteristic of this circuit. Okay, so how do you determine differential gain? We already know its differential gain is this, right? So we need to find out transconductance at equilibrium state. So GM1. So first of all, for part A, I think I have some space. So first of all, you need to find out, let's assume GM1 equals to GM2 at equilibrium state equals to GM. So we know that this is at IDQ of 1/2 ISS, which is 0.5 milliamp. So you need to find out where your quiescent point is, which is 1/2 of the total tail current. So this will be, I already have my device parameters, mu and Cox, W over L, times the current IDQ, which is 0.5. You simply insert the numbers, and we get this as 1 milliamp per volt. Okay? So once we have this number, we can, the second thing is to determine the output resistance, RO1, RO2, and equals to RO4 because they're taking on the same current, which is lambda. They're having the same lambda, IDQ, over 1. So this will give me 10 k ohm. Therefore, you should be able to obtain your differential gain. Differential gain is minus GM1 times RO2 in parallel RO4. You can do 2, it doesn't really matter. The same results. So we get a differential gain about 10 volt. There shouldn't be a minus sign because I'm only taking out the opposite side. So it's already inverted back to positive. Okay? So for common mode gain is this equation. So let me write down here B. for ACM is minus GM1 over GM3 divided by 2 times GM RSS. Okay? So we know that the GM1 equals to GM3 because if you're using this equation, even though it has the same current, it's mu n and W over L compensate each other. So now we know this is a 1 minus, and this is approximately as 2 times GM times RSS. I forgot to give the RSS number. You simply assume your RSS, let's say RSS is 1 k ohm, 10k, sorry, 10k ohm. Then your common mode gain should be minus 1, 2 times, you get it, 10. So that should be minus 0.05. Okay? 2 times. So you can actually get a very low common mode gain simply by doing this active load operation, active load structure. So lastly, let's look at the last part, which is what is its equilibrium state, output equilibrium voltage. As I said, it's VDD minus a threshold of P minus a VOV equilibrium P. So I forgot, did I give this threshold? So in this case, I have a threshold voltage N equals to P 0.5 volt. So you simply just insert the number, it's 3 volt. Once again, VOVP will then determine by equilibrium P will be determined by ISS mu P Cox W over L 304. So you simply insert the numbers and then should be 3 volt minus 0.5 minus 1 volt. So it's balanced at 1.5 volt. Okay? So this exercise simply lets you know that, once again, if you're using an active load, it could actually maintain your differential gain. I will still have relatively high differential gain set by GMRO. And I have a differential common mode gain being effectively suppressed to a fairly low level. And also, we could actually set your equilibrium state output level, this voltage level, to a well-determined level. This is very important because typically in integrated circuit, if you don't want to add level shifter like capacitors, this DC level will then be determined as the input operation range. So you want to set it to the next stage input range at the middle of your input range. So the well setting of this point is very important to subsequent circuit designs. Okay? 好，那我们先 take a break for 10, and then I'm still going to leave this blank. Someone wants to come and help with this thing? No one? Okay. Oh, someone's, yeah, come on. Great. So I can take a break. 大家可以休息，我们等他写完，我们再讨论他对还是错。应该是对了。请他画那个 maximum 跟 minimum。那我稍微讲一下，就是在他解答的时候，我稍微讲一下，就是如果你做这个 active load， 最大的好处，我刚才有讲到，就是说除了这个，通常我们一般来讲 就是做 conversion， 就是你希望从 differential 变成 single and， 这是第一个。第二个呢，是你希望设这个点，这个点非常的重要，因为我如果可以 determine 它在哪里，就是我可以透过 first order 设定，这叫 first order 的 equation。如果你两个点啊，如果你不是，就是如果你是 active load 的话，我们之前讲说它交错的位置是有非常多不确定性。那这个的话呢，就是比较好设定，你可以设到你想要的位置，不是 second order effect 去设它的话，那你就可以决定下一级 input stage 的 balance point， 比较好设计。 Let's continue our discussion. I'd like to thank the volunteer, which answered the question very good. It did very well. On the transfer curve, we know that, let me sort of illustrate what actually happens, is that when you're at this, there's 3 regions. If you look at large signal, you want to separate them in 3 regions. In region 2, of course, there's small signal gain, so you have linear response. There's no problem. So you want to find the extreme case. What is the extreme balance point at these, when you tilt it to one side? So when I tilt it to the left, meaning that all the currents going to this direction. So for region 1, let me use a color, different color. So let's say region 1, I'm using, we already discussed 2, so let's just say for region 1, what happened is that all the current, this is ISS, right? Your M1 takes on all the current. That would then lead to, you're only supplying half of the current, so the rest should come over. This is 0. ID2 equals to 0. So then the maximum current that will be flowing is all of them coming in, so the current is flowing in this direction, which is 1/2 ISS. That's why you get the maximum of 1/2 ISS times RD. Okay? So in the reverse direction is, let me use the blue. In the reverse direction is this ID2 will then become ISS. This is ID1. So in region 3, which is highlighted in blue, will then give you ID1 equals to 0. So there's no current. The current will then be flowing in the, so you're taking all, so aside from the original 1/2 ISS, your current is actually flowing this direction with 1/2 ISS. Therefore, your current, because it's flowing in the reverse directions like rectifying circuit, so you see the minus. So let me just make sure that everyone sees this well. Okay? So your minimum level will be minus, so it will be a symmetric structure. This is very good. For the half circuit, what happened is that for differential signal, you're not actually concerning with these terminals. So the half circuit, I'm simply going to tell you what the half circuit will look like. The half circuit will look something like this. Virtual ground at the bottom. Remember, this is still virtual ground. So your half circuit will look something like this. Equivalent half circuit. 1/2 EID, 1/2 EOD. And this is 1/2 RD. The reason why it become 1/2 is that you will see that it doesn't matter whether you go to the left or to the right, the middle point will always be the same, will be the balance point. So for this type of circuit, you can actually see an equivalent circuit looks something, then this will be AC ground. If you look at to a loading, so for small signal, you actually have a maximum gain of GM, 1/2 of GMRD. My RD is actually cut in half. Okay, good. So there's a reason why people would like to do circuits or make circuits with 1 resistor instead of 2 resistors. We're going to talk about that in a little bit and explain why. So I want to spend my 15 minutes on discussing the concept of single-ended output and differential, fully differential, because we didn't actually talk about that in very detail. So if I have this circuit, for this particular circuit, there's 2 possibilities. One is fully differential. So for fully differential, remember what fully differential means. So for fully differential circuit, what happened is that you define your output like that as VO2 minus VO1. Okay? So let's compare what happened. What is the actual noise propagate to the output if you're doing fully differential or you're doing single end? What does the actual common mode get? So if I'm using this circuit as an example, I'm doing either way. It's either fully differential or, so fully differential is the second. One is that if I want to take out only one, there's another solution is I'm simply taking out VO. That's called a single end. So if I'm not doing conversion, I'm simply just compare the two. Single-ended structure. Okay? So if you look at VO for the left, for the single end, for the single end structure, my output, remember when we write down is, it will be determined by the gain on the right. Let me just write down GM RD for differential. It was subject to two signal. My input Vin2 will be VICM plus minus 1/2 VID. Okay? So the corresponding results by this. We know that the common mode will be 1 plus twice GM. I'm just going to use GM RSS since I'm only having N-channel devices. And the top will then be GM RD times VICM plus my differential gain, which is GM RD times 1/2 VID. Okay? So by our understanding of this simple differential pair, we know that if you inputting common mode signals will be amplified by this factor, differential will be amplified by this factor. So to actually determine, once again, this is how much noise being amplified. This is the common mode gain. This is the differential gain. So we're going to redefine our common mode gain. The common mode gain is when VO when differential is set to 0, because I don't have differential term in the output, against VICM. So if you want to look at common mode gain, is defined as output term, your overall output when differential is set to 0. When differential is set to 0, we know that the common mode gain is as regular. So remember this definition. I probably have a minus sign in the back. So for differential gain, is defined as input differential, output when common mode input is set to 0. So the way to separate this, when you lump your output with both common mode and differential, this is the results. Okay, so this would then give me 1/2 GMRD. The minus sign cancel, I should say. There should be a minus sign in the back because I'm applying negative on Vn2. So there's a minus sign. Okay? So your actual gain is being reduced by half. We already discussed that. That's the single end. That's how you get your CMRR. Okay? So we actually get a CMRR of GMRSS. About GMRSS. Okay? I'm ignoring the 1. So let's look at if I'm using a fully differential architecture. If it's on the right, what happens is that your output is no longer a single end output, it's differential output VO1 minus VO2. Okay? So then this, this is VO1, this is VO2. So I'm simply gonna write down VO1 and VO2. So VO2 minus VO1. So what happened is that you simply just going to use, let me write it down. VO2 is RSS VICM plus minus GMRD minus, that's my VO1, VO2, and minus the same thing. I'm going to explain just a little bit. And the only difference is that the gain is the same. And then this will be positive instead. Okay? So because if this two is identical, then I could cancel them. This simply means that if I want to be precise, this is the left one. So this will be, in this case, I'm going to label it as the transistors on the right. And this will be the transistor on the left, let's just say. RS is the same. Okay? So for fully matched, we call it fully for, if we consider fully matched circuit, meaning that your transistors, your resistors, loading resistors, transistors are exactly identical, then the left will cancel each other. So what you're left with is GM RD VID. Okay, so this is the results under fully matched assumption. So for fully matched, let's go back to this. So your common mode gain would then be VOD at VID equals to 0 divided, because my output now is VOD, VIC. So if you look at this equation, your output, if you're doing fully differential, the left cancels the right. It's independent of VICM. If you set VID to 0, this is 0. So you actually have a common mode gain. This is ideal. I have a common mode gain which is 0, meaning that any noise come in will get shunt out 100%. Right? It will not be amplified at all, and it will be turned to 0. That's the benefit of doing fully differential, and I'm still getting my differential gain. Right? My differential gain by this case is GMRD. So I'm following this. It's independent of common mode gain, so it doesn't really matter. So you get the full differential, and you actually block out all the noises. Okay? But this is based on one assumption, which is a fully matched circuit. But in most cases, there's some small little difference. Let's say if all of the things are the same, the main difference, let's say, I'm just going to do an example. And this also always happens. If there's we call mismatches in R. So I have R1 equals to RD. RD2 equals to RD plus a small little variation. Okay? If that's the case, I'm simply going to repeat this equation. What you get is something like this. So instead of fully cancel the left and the right, your VOD would then become 1 plus GM. You're still subject to this degeneration attenuation factor, but then the top will then become GM delta RD. The right minus the left, delta RD. So if there's a little mismatch between the two, you then still have a VICM plus GMRD. Okay? So if you consider a little mismatch, then I'm still going to experience a common mode gain, but a much less common mode gain, which is GM delta RD 1 plus 2 times GM RSS. That will be my new common mode gain. And typically what we do is that you do it this way. You sort of benchmark that to okay? So what does it mean? It means that this is the original, if you consider single-ended common mode gain, and then it can be reduced by how much a mismatch can be obtained. So, okay? So this example is just to show you that you still want to make sure that you have this tail, even though we can cancel it through fully differential because this noise can propagate when there's mismatch between the two. It's like my identical twins are not of the same height, so that would it come into some sort of to affect my impact on the signal you want to pick up. So if you have really identical characteristic, then it doesn't matter. You can cancel each other out perfectly. But if there's non-ideal factors like mismatches in the pair, then these are the things that to be considered. So you still want to make this as high as possible, the attenuating factor by this current source. Okay? So I think my time is well up, so I'll let you get ready for the quiz. I'll see you next week then. Bye.